So the elegant diagrams basically was designed to address metal oxide, the reduction. Then you can find the same diagrams with the sulfides and fluorides and many other compounds. But the thing is that you have this metal oxide here. So this is the free energy of formation. So this is only thermodynamic kind of consideration, of course. Now we are working closely, let's say at 1,000 degrees, right? And now we need to check if we can reduce this with hydrogen. So in a simpler case, if the hydrogen, if the water formation, because the formation is for the oxide, in this case, when you react this, you get the oxide. If the oxide formation, this is of course negative values, so deeper the value is more stable, okay? So for example, the oxides that are formed here, like, I don't know, alumina or titanium oxide, all these are very stable, so therefore they are very negative in their energy of formation. And what we look at here is if the curve for the H2O formation is preferable from the energetic point of view to the metal oxide that we're dealing with. So if so, if like in this case, and this is the case for copper oxide and also nickel oxide, and so if this is the case, so then we can run the system, in this case with copper oxide, and reduce it in situ in the system before the growth. And this is ideal, because we prepare the system, the metal just before the growth, right? And, but this helps you also to screen what metals you'll be available to work with, and what metals you will be needing a completely set of parameters. For example, if you want to use iridium, okay? Iridium oxide is somewhere very, very low. Iridium oxide, why iridium? Iridium, it has very low solubility of carbon as well, like copper. And people have grown graphene on the iridium in the UHV systems, with the high vacuum systems. But in order to work with iridium in a system like that, you will be needed to find a solution for the oxide, because the reduction of the oxide with the hydrogen will not be enough. You will not be able to reduce the oxygen in this oxide. And therefore, this simple scheme helps you to screen materials. In this case, metals, but metals for the growth of graphene. But it can be in many other systems. Yeah. So this is about the copper and the nickel. In addition to that, in special for the copper, I told you the copper has a melting temperature very close to the growth temperature, 1084, I think. Anyway, very close to the growth temperature. So that means that if you anneal it in H2 before the growth, in order to reduce and clean the surface, you also, at the same time, cause grain growth in the nickel, in the copper foil. These copper foils are polycrystalline. Polycrystalline means that every grain is a single crystal. But in the as received foils, you get crystals of, I don't know, 10, 20 microns. copper. And the crystal growth of the graphene might be related to the crystal size, to the grain size of the metal. So therefore, when you anneal it at high temperatures, and in order to clean the surface, to reduce it, and also to clean any organic matter that you may have there, you also increase the grain growth, which is also good to have. Okay, so this is a very simple case of CVD on metal, and that's why copper and nickel are so famous and so often used to grow graphene, because they lead to good results, and also they can be cleaned very easily, in contrast to other metals that may lead to good results, but are more challenging to work.
Sir, water vapors are there, it will be hard to create vacuum.
Sorry, yes?
Water vapors are there, it will be hard to create vacuum, right?
No, but we are talking about a very thin surface oxide. So you have, first of all, the vacuum here is a low vacuum. Low pressure, that means that the base pressure usually in these systems is about 10 to the minus 10 milliton. It's a low vacuum system. Low pressure, low vacuum. It's hard to grow materials in these systems when you have a higher vacuum. I mean, flow is hard for the pump. Because here you flow much more gases than in systems like MB and so on. But so yeah, so the water is not a problem. Okay. So this is a simple example about the problems that you may face even before you grow. And for example, in our group, when I was a postdoc, we had a problem with the copper surfaces. We didn't know what happened there. We didn't get growth, any growth. And it turns out that at that time, some of the foils came with a coating, a protective coating. But in our case, it was the metal coating of some metal, some chromium oxide or something like a very thin layer. And chromium, you cannot reduce by that. But also chromium I'm not sure how it will behave in the catalytic effect, but chromium you cannot reduce. The chromium oxide also is a very stable oxide that is hard to reduce, especially with the H2. So therefore we had to wet etch before and then okay. Now to TMDs. TMDs, I showed you that the most common, basically the 99% of the growth done today of TMDs is done with this methodology, right? The first paper that was published more than 10 years ago, basically with the powder precursors, metal oxide precursors that are not suitable in principle for CVD because they have very low vapor pressures. And therefore it's hard to study the growth of these materials. And so then, as I told you, one of the ideas to improve the growth, but still having this metal oxide. By the way, why everybody uses this metal oxide? Why not using metal organic, metal alloy? Why everybody uses this metal oxide?
Oxide may grow easily, sir, but the other may go under embedded interaction.
groups is a good way to get fast results with fairly good domains, TMDs. Fast with large domains, and yet, if you want to study the growth, if you want to study the growth mechanism, with this precursor you cannot do that because they are nearby the growth substrate. You have no control over the flux, over the delivery of the metal precursor to the system, to the growth area. And nevertheless, people have came up with ideas like the ones that I discussed before. So the first one that I discussed, for example, is to work in a condition in which we know that we have high evaporation rates, okay? But then to confine the area of the growth. So then here we have a stable and constant concentration of the precursor, very high. Here is in an area that is not confined. But then in the rest, so we have a drop in the precursor as a function of the length. And therefore we can, by that, we can basically control at some extent. Of course, it's not perfect. It took a while to realize, but you can control at some extent the delivery of the precursor to the confined area, okay? And avoid the formation of multi-layer regions in the important areas. Here, the important area is the confined area. Now, with the seeds, the other methodology was to remember the seed growth. Now, for the seeded growth, so the seeded growth, for example, we used metal dots, metal seeds, gold seeds. And what happens is that in this case you need to work in the opposite regime. Here we work in the large flags, okay, flags, pitch rate, large, and here we work in a regime that we know that we don't get any growth in these areas. So we work with very small fluxes. Because if you compare that, again I'll do the analogy to homogeneous nucleation and heteronucleation, right? If you have homogeneous nucleation or heteronucleation on top of a substrate, okay? The stable nucleus size that is needed on the heterogeneous case is much smaller than the one that is needed here, right? And therefore, you need, in order to selectively, so we do the analogy. So in our case, the seeded substrates are the heterogeneous substrate, and the homonucleation is like clean substrate. So in this case, when we grow like that, we don't want to grow on top of clean areas. This is not how to achieve, because in general, the stable nuclei on these areas needs to be larger than the one on these areas, right? That's the whole idea of homonucleation against heteronucleation. So that's why we use seeds with different distances, and we can basically control the domain size. And but one thing that we didn't take into account is the interaction of the metal seed with the TMD. So in our case, we use gold. We use gold for several reasons. We know that gold has no solubility of sulfur or molybdenum into it. We know that sulfur has a very strong bonding to gold. So we thought that this is a good idea to start with, a good method to start with. But the problem was that when we did it at high temperatures, I don't remember the ranges, but it was, I think, above 850, what we got is a surface diffusion of the gold on the TMD domain. So we got triangular domains, and when we did PL mapping, what we saw is that we have different areas, very clear different areas with different PL. And this different PL was because these areas were full of dots of, they were full of gold. Small concentrations, but gold only in these areas. And why in these areas? We assume that only in these areas because these directions grow faster. So we believe that first these corners grow, and then the rest is incorporated, and by then we have enough time and temperature for the gold to diffuse only to these areas and to grow with the material. So when we work with the seeds, if you work with the metal that has, like gold has a low melting and it's not so stable, you need to think about, in general, you need to think about the reaction of the seed with the TMD and different effects like this one, like the surface diffusion and so on. But this we could solve very easily by reducing a bit the temperature. Reducing the bit the temperature inhibited the diffusion of the gold, and that made it. It was a nice story. Now, the metal organic. I didn't talk too much about metal organic, but metal organic, as I told you, usually leads, if you don't use any trick, metal organic deposition of the TMDs will, in most of the cases, end like a nanocrystalline film. That means low quality, then that means not as good. And this is because of several reasons. Two main reasons are, one of them I told you about is the possible carbon contamination from the precursor. When we have a precursor that contains carbon, metal organic. The other reason can be that these precursors start to decompose at low temperature. They start to decompose at low temperatures. That means that we have a lot of nucleation at the surface. That again is very hard to control, even if you reduce significantly the flows of the metal organic. And the way that we solved this issue was by a method that you can use for other crystals as well. a method that we relate as growth and H. Growth and H. So why? Because we start the nucleation, let's say in this case, domains. So you have carbon, you have some nucleation, you have some very defective domains, and you have carbon. The carbon induces nucleation by itself, right? Like the seeding of nucleation, and therefore it creates defective domains. All these you basically we'd like to get rid of them. And that's what we did with introducing H2 or O2. Okay, why? Because again, the oxygen will react with the carbon. So that's to leave CO2 and CO, both of them gases that are easily exhausted.
Sir, what is forming in a triangular shape surrounding the gold seeds?
So this is not related to gold seeds.
No, previous, I'm still in the previous.
Okay.
The previous gold seeds. So how it is forming only in the triangular shape? And are they mono layer?
It was mostly monolayers. Sometimes we got here add layers, which is something very common to get in when you use metal oxide, because it's hard to control the thickness of the oxide in the beginning. So what did you ask? So we assume that this growth is just faster, and therefore you don't have enough diffusion of gold to these areas.
I'm asking how is forming three directions? Like what is the shape of it?
Yeah, this in principle this is truncated triangles. Right, so you have the sulfur, the molybdenum, the sulfur, the molybdenum termination. One of them is more stable than the other, so in most of the cases it will prefer to be at the edge. Okay?
Nucleation will happen only after passing the sulfur or before passing.
Usually in this growth you have both precursors all the time in the gas phase. But with the metal oxide, it's very hard to control the flux of the metal oxide, so it happens a lot that you have too much of the oxide in the nucleation stage. And if you have too much of the oxide, you may end up with a lot of particles, or as I showed you, of metal oxide before they are sulfurized. Okay? And the same here, the add layers. The add layers presumably are formed because of having a large amount of oxide in the beginning, in the center of the nucleation stage.
Then here we can remove the, like previously you told that you can add hydrogen and you can remove the oxide before the process.
Okay, but the thing is that you can in principle deposit nanostructures of metal oxide and then reduce them. That's what you said?
Yes, sir. Before reaction we can remove the oxide.
Yeah, but then you will have the molybdenum and you will have similar results. Because if you could form conformal metal oxide layers, so maybe. Also, if you could form conformal metal oxide layers, you can react them with the chalcogen to form conformal molecule. In this case, when you have not controlled the position, you will end up with different structures, even if you reduce them. Okay? And molybdenum, I think we need to check in the elegant diagram if you can reduce with hydrogen at these temperatures. Maybe you can. Maybe it higher. But I was talking about, so with the oxide, with the oxygen, you get rid of the carbon, but not only the carbon. With the oxygen, you also get rid of the defective domains. Why? These are MOS2 or tungsten disulfide that at the temperature of the growth, they are supposed to be stable. But think about that first. They are monolayers. And second, they are defective. And thus, they react with the oxygen to form both sulfur oxide, that is a gas, and molybdenum oxide, that is not a gas, but at such temperatures, we know that it evaporates, like in the metal oxide CVD. And in this case, it's a monolayer, so for sure it's not stable. Okay? So that's why inducing very small amounts of oxygen helped us to clean the surfaces and allow for the growth of high quality material with larger crystals. Okay? Questions? That's it.
Sir, one thing, sir. Sir, regarding the formation of the mole patterns, so in MB, can we create mole patterns?
Okay, so he is talking about we'll talk about heterostructures tomorrow, but yes. Heterostructures, mole patterns are patterns that are obtained when you take two layered materials and not even the same material, and you place them one on top of the other, but with different registry than the one that you should obtain. I don't know of any method that gives you a consistent molecular pattern. I mean, you can grow A-B stacking in graphene, of course, and there are some reports about specific registries. I don't know about that.
So by using MB, can't we grow in a different orientation?
Why?
Just to create mole pattern.
No, but why do you think that MDE will give you the option to rotate the layer? What is the what is the trigger for that? Should be an energy gain in rotating these layers. But we know that it's not, right? We know that these registries are not the most stable. So why during the growth do you think that you can get a specific registry? I don't know. I don't know of anything in MBE for sure.
It's like, sir, to have a substrate at the bottom. So once we grow this MB, and then can't we rotate the substrate and then we can grow another layer?
You can grow one layer here and one layer here and then rotate it.
No. Growing one layer on substrate,
Yes.
and then just rotating the substrate. So already a layer was grown. And that layer, if you grow another layer, so then that will create a.
But the precursors for the another layer, they are elemental precursors in MPE that will reach the surface, and they don't care if you rotated the substrate or not. They don't feel that. If you take a silicon 111 and you rotate it, it will grow the same germanium methyl germanium layer after that, with the same register. You will not change the crystallographic registry because of that. Any more questions?
Sir,
Yes?
why don't you consider chemical vapor transport for this?
Oh, chemical vapor transport, I didn't talk about that. Chemical vapor transport is basically the method in which the most famous method to make 3D crystals of 3D crystals of 2D materials. Do you know how CVD works?
Two different temperatures.
So in CBT, what you do is you take an ampule, usually quartz ampule, you put all the elements in the right ratio according to the stoichiometry, and then you seal it in vacuum the ampule, meaning that you put the ampule, you connect it to a vacuum pump, you pump it down. So this is the ampule, here is open and here is closed, of course. And here you have all these ingredients. And while it's pumping, with the torch, you seal the ampule. So the torch will melt the silica, and because of the vacuum, it will close and seal the ampule. So then you will have all the ingredients needed and everything in vacuum. Then you load it into a reactor, and you heat it up, and you leave it that then for at least 12 hours, usually a few days, and then you get this type of crystals inside the ampule. You need to break the ampule and you take out the crystals. This method, I don't think that is good, so good for thin films.
Like kind of two-zone furnace you can build in that furnace.
But this is very similar to the systems that are used. I mean, the system that I described here, for example, here, for example, you can use a two-zone furnace in order to heat the hydrogen and the metal separately. We do it with two different heating systems, but with only with one. Basically, you have two heating areas and temperatures. So this is something that all the time is done with experience.
What I was trying to say is like doing I get the bulk powder or something. I try to melt the bulk powder. That will be in high temperature region. And I'll keep my substrate in the low temperature region. So that I try to transfer.
Yes, people have tried that. But again, it's very hard to control. There are some reports about that. But here, another question. So most of the growth, MO, constant related TMDs, and very few works on tantalum, for example, niobium, selenite, sulfide, by CVD. There are some, but not a lot. Why do you think is the case? We go back to the first thing that I shared with you in this meeting, Elegant diagram. These metals have very, very stable oxides. Reacting them with sulfur will not do much. So even if you start from a precursor, for example, from a metal organic precursor, and you work in a metal organic precursor tantalum, you can do it. I mean, people have done it. And you need to take into consideration that the synthesis will be much more challenging, because every residue of oxygen will react with the tantalum, with these metals. And this can kill you the growth, even when you start with a precursor that is not supposed to be oxidized. Okay? And this is also the reason why you cannot grow some of the TMDs with the metal oxide, with their metal oxides. Some of these metal oxides have very, very, very low pressures, even at the growth temperatures. You cannot evaporate them in an efficient manner in order to get any growth. Right? Any more questions?
So the vertically aligned TMDs, can you just give an idea? Vertically aligned TMDs are there.
Yes.
So will there be golden band between the substrate and the first layer of the TMD?
Again?
Like there's a vertically aligned TMD.
Yes.
What will be the interaction between the substrate and
That's a very good question. because the vertical layer, the edges, in principle, they have dangling bonds, always the edges, and the dangling bonds. So in principle, they can attach to it. I don't really know what is the nature of the interaction between the vertical and the horizontal. But they are stable, they don't peel off. That I can tell.
How to grow on decision by saying how to go and grow like the
How to grow? This is the easiest. This is the easiest. You just need a thin film evaporation step to prepare the thin film molybdenum or tungsten. Again, if you want to use tantalum or niobium, you need to get rid of the oxygen. And during the growth also you need to get rid of the oxygen. But in principle you can do also with that. After that, you load it in the system, you react it with sulfur and with sulfur precursor, and usually there is some H2 and inert gas, and that's it. Very simple. This growth mechanism is similar, the concept at least, with the growth mechanism of silicon thermally oxide silicon oxide, silicon. Do you know what is the growth according to the Deal model? So basically, it's not epidaxy. It's not epidaxy at all. I told you that the oxides are amorphous. What's happening is that you start from a silicon, so you have silicon dioxide formation. Here you have the silicon. So here you have the gas, right? So basically you have three regimes. The gas flow to the substrate, the diffusion of the oxygen entities towards the interface, and then the reaction. Right? This is the basics of the modeling of the thermally grown silicon dioxide. You can find it everywhere, it grow a model. And therefore, assuming steady state, you can compare between these entities and these fluxes. You have a flux in the gas, a flux of the diffusion, and a flux of the reaction. Right? So you can extract a lot of very important parameters out of them in order to control the kinetics of the process. And this is it is still working in the industry. They don't use it as a gain dielectric anymore, but they use it in a lot of processing. Okay, so the same for the molybdenum or tungsten disulfide in this case. You have the molybdenum that reacts with the sulfur, right, to lead MOS2. So you have a layer of MOS2, and then the metal, molybdenum tungsten. But then the sulfur needs to diffuse here. So that means that also in the silicon, when this layer, the silicon oxide layer is thick, the limiting rate is the diffusion rate, right? Because it's too thick. The oxygen needs to diffuse a lot. But when you are talking about very thin layers, the limiting step is the reaction, because the diffusion is very fast. So similarly, in the MOS2 case, for the vertically aligned something similar, the same principle.
More thinner the layer. The more thinner the layer.
Sorry?
The more thinner the layer.
What do you mean? If you have very thin layers of less than 3-4 nanometers, you're supposed to get planar films. For thicker films, you get vertical. Okay? But planar films less than 10 nanometers is very, very hard to get by standard processing. You can get it. It's challenging. Any more questions?
Can you explain how to grow unmatched using seeded?
Seeded code? Yes. So you can use the metal oxide precursors. Okay, and here why for the seeded growth the metal oxide precursors work well? Because with these precursors you can get actually a low density of nucleation, and therefore ensuring that the nucleation is also only here. So basically you start with a silicon or whatever substrate, then you do photolithography, imaging lithography, evaporation, metallization, and liftoff, and then you eventually get micron scale. We use micron scale seeds. Now, if we try to use nanoscale seeds made by imaging lithography, the problem, you need to remember that you then need to take this substrate, load it into the system, heat it up to a few hundreds of degrees, and if you have a very small dot, it will be wet and you will lose it. Okay? That's why you need we found that we need at least 2 micron size seeds to seed. Of course, you can solve this issue by other methods, but this is what we do there. After having the seeds, you load it into the system, and in this case, we use the metal oxide. We use the metal oxide under conditions that we knew before, that we are not supposed to get nucleation on clean substrates, and only on the seeds. Because if you get nucleation everywhere, if you get too much nucleation, if the density of nucleation is larger than the density of the seeds, you're going to get growth everywhere, not seeded growth.
So, what are the seeds composed of?
In this case, gold. Metal, yeah.
For almost all.
Yes. And I explained why we choose the gold, because gold and molybdenum, they don't react, and molybdenum, gold has no solubility of molybdenum, and neither of the sulfur. And the sulfur attaches very strongly to the gold. Actually, people use gold as a catalytic surface for the growth of TNTs. Even very large crystals, on single crystal gold. But then again, you're with the same problem of the graphene that you need to transfer it.
Like we used copper for graphene, we use gold for chemistry.
Right. But it's not common. It's less common than the other methodologies.
Here you explained that the sulfur aesthetic use to the market.
Yes.
So it is, in that case, we need to consider in which way we are flowing the gas, whether it is in the lateral direction or
No. Gas kinetics allow you to, the gas will not feel so much. I mean, as long as you have the right concentration of gas molecules, but also on top of the surface, it doesn't matter.
So flow direction is not important.
Not in these cases. Or at least not as important.
And so in one case you explained to control the flow rate of evaporation rate of metal oxide, we use a mica to control the flow
No,
rate.
but this is not to control the evaporation. We don't control the evaporation. Actually, in this case, we let it evaporate a lot. But we control the diffusion of the surface of the precursor along the surface.
Like how is that set up made? How is mica suspended?
It's not suspended in there. You attach it physically, so it has a few microns gap. This is the confinement. You can build something fancy, but actually mica is not so flat. Mica is also a layered material, very complex one, with a lot of elements.
This one is heterogeneous nucleation.
Sorry?
This one is heterogeneous nucleation. Old.
Yeah, the seeding. Well, heterogeneous nucleation in principle happens on the surface as well. But here I did the analogy of taking the clean surface as the homogeneous and the seed case as the heterogeneous.
If I see it with the same material, will it call it will be homogeneous, or why when it will be homogeneous nucleation? What is the basic difference between this one and this?
No, it's different than for epitaxy. Homogeneous nucleation means that the nucleus forms without any support. Like when you're nucleating and growing something in liquid, it grows in a solution with no support. Heterogeneous grows on for example, if you put a hair in the solution, it will preferable nucleate at the support, at the substrate. In this case, the hair. Right?
So all seeded growth are heterogeneous. Chakravsky.
Yeah. Well, Chokrovsky is heterogeneous. Yes. Basically, it's different because you don't have nucleation there. You don't nucleate anything. In Chokrovsky, what you do, you have the clean crystal plane of the seed. You attach it to the melt, and you have a single crystal growth by attachment to the preferred sites. Okay, because high temperature will melt, a lot of diffusion, also a lot of thermal heat dissipation, a lot of processing there. But you don't nucleate anything there. It is already nucleated. You're growing. The seed is basically your nucleus. Any further questions?